So we learned about meromorphic functions from the extended complex plane. So we say f is meromorphic which I'm denoting like this, which is C, where we augment infinity. And it is meromorphic from the extended complex plane if and only if it is meromorphic. And f of 1 over z has either a pole or 0 at 0. Okay, theorem. If f is mirror on the extended complex plane, definitely need new pens. Then it's a rational function. Okay, proof. All right, first thing to observe is that if we have a meromorphic function in the extended complex plane, we have only finitely many poles. So claim okay, why so? Well, first thing to show in order to prove the claim is that if we have infinitely many poles in a bounded area, then they're going to have a cluster point, and if they have a cluster point, we'll get a contradiction. So suppose not, and we have infinitely many poles zk, and also suppose they have a cluster point. Let's call the cluster point z tilde in the complex plane. Okay. Well, what would we know about the cluster point? So let's put z tilde here. So we have this sequence that tends towards, let's say this is z1, z2, z3, and so on. That tends towards this cluster point right here. So what properties would we expect of a function f at z tilde? What would we expect for function f at z tilde? Yeah, you would have to have a pole, right? Then z tilde has to be a pole, because if not, it would be bounded in the punctured disk around z tilde, right? Yeah? Just write bounded near z tilde, which is impossible because no matter how smaller neighborhood around z tilde we put, we're going to have a pole inside this neighborhood because it's a cluster point of poles, so it can't possibly be bounded there. Yeah? Is that making sense? Okay. So it has to have a pole there, but what does it mean to have a pole? So this means that 1 over f of z has a 0. At z tilde, right? Yeah, but 1 over z of z will also have a 0 at every one of these poles zk, right? Because f blows up at zk, right? And has zeros at zk also. So z tilde is a point which is a cluster point of zeros, yeah, for 1 over f of z. Yeah, which is impossible, because as we've learned, if we have a cluster point of zeros for a holomorphic function, then it has to be identically equal to 0 in a connected set. Yeah? Zeros are isolated. Is this coming back to you? Is this making sense? Yeah? And thus, z tilde is a cluster point of zeros of our function 1 over f of z. Contradiction. Because we're assuming we have a non-trivial function. Okay, so we cannot possibly have a cluster point of our poles. Yeah? But if there are infinitely many of them, then if there's no cluster point, then they have to go off to infinity. Then they have to go off to infinity. Yeah? Because in any bounded region, there has to be at most finitely many zeros. Yeah? So this means the cardinality means the number. So number of zk inside the ball of radius r around 0 is less than infinity. So we have to have for some subsequence let's call it zkn. Do I actually need a subsequence? No, I don't think so. So there's no harm in taking one because we're still going to get a contradiction, but it's not needed. So zk goes to infinity as k tends to infinity, because if this was not true, then there'd be a subsequence that remains bounded, and that would contradict this. Yeah? So zk goes to infinity as, consider this thing, but then one over zk tends to 0. Yeah? And let's call it g of z which we're going to define to be equal to f of 1 of z, is a meromorphic function, yeah, which has either a pole or it has a 0 at 0. Yeah. And so 0 is a cluster point of poles of our meromorphic function g. We just learned that that can't happen. We cannot have a cluster point of poles. Yeah? Contradiction. Okay, so we definitely have just finitely many poles under this situation. All right, so now we're going to try and, okay, so we have poles. Let's label them Z1, Z2, all the way up to Zn. Yeah? Each one of these poles has its principal part locally. So for each I up to n, then we have that locally, so in some little neighborhood around each of these guys, which I'll do in a second, f of z has a form like this. Some I is equal to 1 up to, let's call it qn of a to the, let's not use I, let's use k. A to the minus k, z minus, let's do this better. So we're doing this for each one of these poles. Let's pick the pole. Let's call the pole zp. So z minus zp to the minus k. This is the principal part. And these coefficients will depend on our choice of whichever pole. So we're going to put a p here to indicate that the coefficients depend on that particular choice. Okay? And then we'll have some nice holomorphic function. Let's call it h of p of z. And this is true for z inside some pole of some radius, which depends on rp. So rp around the pole zp. And this is true for each one of the poles. So p is equal to 1 to all the way up to n. Yeah? Cool. So we have this structure. And what we're going to do is we're going to strip away the principal part, this part, away from f, and then see what happens. So, well, we're going to strip away the principal part. We're also going to strip away the pole at infinity, or the 0 at infinity, whatever we have. Right, because one of our poles can be at infinity, right? Because we have that f is extended, is meromorphic on the extended plane, if and only if f of 1 over z either has a pole or a 0 at infinity. Yeah? So let's assume for the, because it's the slightly harder case. So if f has a pole at infinity, then how can we denote this? Then g of z, which is f of 1 of z, recall, also has this principal part. So let's write that the sum from k equals 1 to q infinity of a infinity minus k of z to the minus k, and then there's some nice holomorphic thing which we'll call h infinity of z. Yeah? That's if f has a pole at infinity. So let us strip away all of this stuff. So let h of z be f of z and minus the sum from p equals 1 up to n, the sum from k equals 1 up to qp of these parts right here. And now we're going to strip away the pole at infinity, right? So if we look at this thing right here, to strip away the pole at infinity, what we're going to have to do is z, 1 over z gets replaced by z. So this z to the minus k now becomes z to the k. Yeah? So minus the sum from k equals 1 to q infinity of a to the minus k infinity z to the k. So all I've done here is I've written what we would have if we replaced, let's use a different letter. If we replace 1 over z by zeta, then this thing would be the sum of this, zeta to the k, h infinity, 1 over zeta. Yeah? That's all I've done here. Because I want to strip away the pole at infinity too. So let me just outline that this thing comes from this thing here, so pole at infinity. All right, let's look at the expression here. So what nice properties will H have? Well, the only singularities H will have will either be singularities of this thing or singularities of F, right? Because we're just adding together these expressions. Well, all the singularities of F occur at the ZP, which is where the singularities of this thing occur, and we actually strip away the singularity, right? So locally around any ZP, there isn't actually any singularity because we've taken it away. Look at this. Yeah? So locally around every single ZP, there is no singularity anymore. Yeah? And whatever we've done at some ZP is not affecting what's happening at some ZP tilde, because this stuff is perfectly fine at ZP tilde. Yeah? You see what I mean? So when we do this thing, when we consider this expression right here, we've removed all the finite poles. There are, inside this expression here, there are no longer any finite poles. Everything is perfectly nice now. Yeah? Cool. And if we look at this thing here, this thing is perfectly cool, perfectly nice, right? As z goes to infinity, h infinity is a nice holomorphic function around 0, so this is behaving nicely. This is just going to something, we don't care. Yeah? And this thing here is just a nice polynomial. Yeah? This thing is a nice polynomial. Yeah? So we don't get any bad effects from this thing. In fact, we have good effects because we know that as z goes to infinity, then f of z looks more and more like this thing, and we're taking it away. We are taking it away. Yeah, that's what we talked about last class, that if we have a pole at infinity, then at infinity looks more and more just like the leading order term of the pole at infinity. Yeah, and we're stripping all of these things away. So not only does this thing have no singularities, but also it turns out to be bounded. It turns out to be a bounded function. Yeah? Turns out to be a bounded function. Because, yeah, if we look at z going into infinity, then z going to infinity is the same as g of z going down to 0, which looks more and more like this, right? So we stripped away all of the blow up happening at infinity by doing this thing right here. Yeah? So H is holomorphic on the entire complex plane and H is bounded. H is bounded. Yeah? Cool. Thus, what do we know about H? It's just a constant function because it's Liouville's theorem, right? Yeah? So by Liouville's theorem, H is constant. So there exists some complex number. Let's call it C. No, let's not call it C. Let's call it W, such that H of Z equals W for all Z. Yeah? And then we can just unwrap this expression. Yeah? So that means that f of Z is equal to this constant function, this constant W, plus all of this stuff, oops, plus this stuff. And if we look at this expression here, this is minus k, this is a perfectly nice rational function, right? Because each individual expression here is a rational function, yeah? And we're adding up together a bunch of rational functions. This is a rational function, yeah? So f is a rational function. When we subtract all of this stuff, then as we let z goes to infinity, then all that will be left will be this guy right here. So as z goes to infinity, this thing will look like h little infinity 1 over z, which therefore is bounded. Yeah? Take any sequence z to k inside the complex numbers such that mod z to k goes to infinity, then if we look at h of z to k, what do we care about? Well, as z goes to infinity, all of this stuff here just vanishes, right? Becomes less and less important. Yeah? So what we're going to have is f of zeta k minus this stuff. Yeah? You see what I mean? That since this stuff here is all negative powers, yeah, as we let zeta k go to infinity, this thing is just going down to 0. Yeah? So we don't care about that. So all we care about as zeta k goes to infinity is this thing subtracting this thing. Yeah? So let's look at it. So this thing, so I'm going to write approximately because I'm just going to avoid writing this thing. It's a long expression. It's this, and then minus this thing. A to the minus k, infinity, z to k, too many k's, m. Yeah? And what is this? This, by definition, is the same as g of 1 over zeta m, like this. And then this thing is the same as to infinity a to the minus k infinity 1 over zeta m. Yeah? Yeah? And 1 over zeta m is going down to 0, right? This is our expansion locally around the pole of g around 0, yeah? So as we get closer to 0 with this complex number 1 over zeta m, yeah? Then we have it inside this neighborhood, so it's equal to this thing plus this thing here, and we're stripping off this thing. We are stripping off this thing. So this thing really is just h infinity of 1 over zeta m, and that's just tending to h infinity of 0, whatever that is. Yeah? So for any sequence zeta m going to infinity, the limit of f of zeta m is just going to go to some bounded thing. Yeah? So we definitely have that it's bounded. Okay, cool. So just stripping away this thing produces a nice function that is bounded and is holomorphic everywhere, therefore is a constant. Therefore we can write it this way, and we are looking at exactly a rational function. We're looking at exactly a rational function. Yeah? Cool. So the only things that satisfy these hypotheses are rational functions. It's a very restricted class. We can treat infinity just like a number. So stereographic projection is as following. We're going to take the complex plane, and we're going to put a ball of radius a half, and it's centered on 0, 0, a half. I'm going to try and draw it like this. And this point here is a privileged point, which is 0, 0, 1. And for any point in the complex plane, we're going to take a straight line that connects this point to the point in the complex plane. So this is the point x plus iy. And that straight line is going to intersect a sphere at exactly one point. At exactly one point. And this is going to define a mapping from us from the sphere to the complex plane. So P, I'm going to let S denote the sphere, or this dollar sign or whatever, into the complex plane. In fact, the extended complex plane, because I claim that this mapping uniquely maps one point to infinity and back. So what point is mapped to infinity if we define the mapping this way? So here is a nice model, right? This is the sphere sitting on the complex plane. This is our distinguished point right here at the top. And if at any point at the complex plane, we take a straight line from that point to the top of the sphere, and we intersect through the surface of the sphere at exactly one point. And that's how we identify points on the sphere with points on the surface of the soccer ball. Start again. And that's how we identify points on the extended complex plane with points on the sphere, i.e. the surface of the soccer ball. Yeah? So what point do we identify with infinity? Let me keep that here. Say it louder. Yeah, 0, 0, 1. So as we want to get closer and closer to infinity, right, then we have to send this thing out. But if you can kind of see here, if we send this thing out further and further, then the line is going to intersect more and more close to the top of the soccer ball, right? And ultimately, no matter what direction it goes to infinity, in the limit at infinity, then the point will be exactly the point at the top. Yeah? Yeah? So this mapping uniquely defines a point to infinity and back. Yeah? What about 0? Where does it map 0? Yeah, map 0 to 0, 0, 0. So as we get closer and closer to 0, our intersection point is closer and closer to the very bottom of the sphere. Yeah? Cool. All right, let's try and come up with a formula for this particular thing. We're mathematicians. We should be able to do this. Yeah? So take x, y, z on the sphere. And then the direction we are going in is the same kind of thing. So direction is x, y, z minus 0, 0, 1, which is x, y, z minus 1. Yeah? That's the direction of this vector right here. Yeah? And then to see where this is actually going to hit, what we're going to do is we're going to have to solve the equation of what we get when we take 0, 0, 1 plus lambda this direction, x, y, z minus 1, and it hits the actual plane. Yeah? And what does it mean to hit the actual plane in terms of what we've written here? So, want lambda such that belongs to the complex plane, right? Which is the same as belonging to R2 cross product 0, because we're thinking of everything in 3D now, yeah? So what would that mean? So what would that mean in terms of what we're trying to solve? So what? So if we look at just the z coordinate, we have 1, we have lambda z minus 1, yeah? So this happens if and only if we have 1 plus lambda z minus 1 is equal to 0. Yeah? So that lambda where 1 plus z minus 1 is equal to 0 is the exact lambda for which we cross through the complex plane. Yeah? So therefore we can solve lambda in terms of this stuff. So it implies that lambda z minus 1 is equal to minus 1. In other words, lambda equals minus 1 z minus 1, which is the same as 1 over 1 minus z, like this. Yeah? Cool. So, therefore, for this lambda that hits through the complex plane, we can just read off what the x and y coordinates are. Right? So, thus we have 0, 0, 1 plus 1 over 1 minus z, x, y, z minus 1 is, well, let's write out what it is. What is this? This is x over 1 minus z, y over 1 minus z, and the other coordinate is 0. And this belongs to, indeed, this thing. So our mapping, we can explicitly write it now as x, y, z is equal to x, let's keep the same type of x, capital X, over 1 minus z plus I, y over 1 minus z, like this. Yeah? So it's not that hard to, I say it's not that hard after screwing it up. It's not that hard to actually come up with an explicit expression. Yeah? Not that hard to come up with an explicit expression for what this mapping is. And this is called stereographic projection. Stereographic projection. Let's think about what it does. This is our soccer ball. Let's make this thing here the top. Let's cut through with a horizontal plane the soccer ball. That's going to give us a circle, right? So we'll have a circle around the outside here. Now, if we consider the image of that circle under stereographic projection, what do you see happening? What would the image look like? It's also a circle. Tell me why. Well, if we slice through with a horizontal plane like this, yeah? If we look from above, what we will see will be a circle, yeah? So the x and y coordinates of this thing around that we slice through, let me try and draw a little bit of it. The x and y coordinates will satisfy the equation of a circle, yeah? And the z coordinate would just be a constant. It'll be whatever height we slice through, yeah? Yeah? And we can kind of see that as we take a straight line going through this, then the distance away from the origin will be the same no matter which direction, yeah? And if we check with our formula, this is our explicit expression, right? So the z is just the height here at some constant, and the x and the y are like this, yeah? And the x and the y on the ball satisfy the equation of a circle, yeah? So this will just still be a circle because we'll still have that this thing squared plus this thing squared will be a constant, yeah? So our geometric understanding tells us it should be a circle, and then the mathematics confirms it, which is what we want to do all the time, right? We want to have a geometrical understanding of what's happening, and then we use the language to confirm it, and this thing explicitly says that if we wrote down this thing squared plus this thing squared, it would have to be a constant, and therefore it's equal to a circle. So our geometric understanding is correct. All right, now, what about if we took a line like this? Like this. If we took a straight line like this, and we mapped it with this mapping P, what would that look like? Try and visualize it. It's also a line. Yeah, it's also a line. Yeah. So if we go all the way round to the bottom here, yeah, it'll be 0 to infinity. Yeah. Because as we take these straight lines, cutting through this line, then they're going to like start off at infinity and they'll go down like this. Yeah? Like this. Okay, cool. So what you notice is if you took this circle around the outside in this straight line like this, yeah, then they cross at 90 degrees. Yeah? They're perpendicular. But the image also crosses at 90 degrees because the image is also a circle and this thing is a straight line going through the circle from the origin, yeah? And in fact, that's generally true, that if we look at this, any two paths on this sphere, and then map it with this mapping P, then the angle of the images will be preserved. In other words, it's preserving angles. It's a conformal mapping from the sphere to the complex plane. Yeah? And that's a harder thing to show, but again, it's a calculation. You can check it for yourself from this explicit expression. What is even more interesting and surprising is that not only are circles like this, where we cut through horizontally, preserved, but if we take any other circle through the sphere, so we slice the sphere like this, for any other circle that doesn't actually intersect the top point here, then the image of that will also be a circle on the complex plane. And that's truly weird. That's not what you'd necessarily expect, but it happens to be the case. And that's also a calculation. So sometimes I'd go through that, but it's somewhat lengthy, so I will maybe add that at the end of the course if we have time. Yeah? And if we have a circle that does cut through this top part like this, then we actually get a line. We actually get a line. Yeah? So this is a surprisingly rich mapping. It has stronger properties than you expect. And these properties are very useful. This kind of stuff, I mean, geographers learn about this kind of thing, because if you wanted to try and map if you want to have a good way to represent a map of the Earth and the continents, then stereographic projection is an excellent way to do it, because it will actually preserve the angles of the continents. So you could have this kind of rendering of the continents on a 3D sphere, and then you can stereographic project it, and you'll see something that is preserved. Obviously, the sizes won't be preserved. Little tiny sizes here get expanded massively, yeah? But angles will be preserved. Angles will be preserved. So if you study geography and map making, then you do a lot with stereographic projection. If you look at the Wikipedia article for stereographic projection, it actually has quite a number of practical applications, because it does this thing of preserving angles and preserving lines and circles. Yeah? Preserving lines and circles. So this is quite a useful mapping, and it's useful for our purposes because now we can think about meromorphic functions on the extended complex plane. We can now think about them acting on the actual sphere, because we can map from the sphere to the complex plane and back. This is a one-to-one mapping. This is a one-to-one mapping. Yeah. So yeah, we can indeed map a circle onto the real line. But it's going to be a less interesting mapping, because what's interesting about stereographic projection is that it preserves angles. Yeah? This is a one-dimensional thing. Yeah? This is a one-dimensional thing, both the circle and this line. So there isn't any sort of angles to be preserved here. Yeah? But yeah, generally, if you think about n space, and you think about the boundary of a solid n ball, think about n space, and you think about the boundary of a solid n+1 ball of a solid ball in n+1 dimensions, then that's going to be something of dimension n. Yeah, and indeed, you can create a mapping from n space onto the sphere. In fact, we denote the sphere by Sn. So that's the boundary of the ball of radius 1, where the ball is contained within n+1. And we write Sn because it's an n-dimensional thing. So, yeah. This goes into the realm of topology, but yeah, you could certainly map n onto Sn with a similar mapping to this. Okay, cool. Let's go back to this. So if we have is meromorphic on an extended complex plane, then you could define let's call it G, and let's take F, let's project a point. Let me call a point now just a point W on the sphere. So we can project onto the complex plane, and then we can pull it back with the inverse of stereographic projection. And let's call this thing G of W. Like this. Yeah. And then this thing is perfectly well-defined mapping from the sphere back onto the sphere. Yeah. And it's a mapping that has this remarkable property that it preserves angles. It's an angle-preserving mapping. If you take two lines on the sphere and you see how they cross, then the image under this mapping G will cross at the same angles. Yeah. Yeah. Which would a priori seem like an extremely restrictive condition. You would think there aren't many mappings like this, but in fact there are many mappings like this, because there are many mappings F which are meromorphic on the extended complex plane. Yeah, and we've learned that they are just rational functions, but nevertheless they have a wide variety of different behaviors, right? So they wrap around the complex plane multiple times. They can do all kinds of weird things. And when we translate them into mappings from the sphere to itself, that means we are wrapping the sphere around itself multiple times. This is wildly not a one-to-one mapping. This is doing all kinds of crazy stuff. This will have poles on the sphere, yeah? But nevertheless will preserve angles wherever the derivative exists. Yeah? So this gives us that there are a wide class of angle-preserving mappings just mapping the sphere to itself. And that, because of Lubbock's theorem, is only true for this sphere, the boundary of a solid three-dimensional ball. It's not true in higher dimensions. Yeah? And we can do this because extended complex, meromorphic functions on extended complex plane treat infinity in a consistent way, just like a point. And here, infinity is just a point 0, 0, 1. You know? So we can do this and not have any issue with what's happening in infinity, because infinity is perfectly good, perfectly well defined, perfectly consistently defined when we have an extended function in extended complex plane, a meromorphic function in extended complex plane. So this really allows us to treat infinity a lot like a number. And this is called the one-point compactification of the complex plane, because we add one point, this point at infinity, to turn the complex plane into something that is actually compact. And we preserve many of its nice properties when we deal with at least meromorphic functions. You know? So many of the issues you have with things not being compact sort of go away when you consider them in this context. So this is quite a common thing to do. There's a lot of theorems and a lot of papers have been written about things like this. Okay, cool. So let me write down some of these words. So S is a way to compactify extended complex plane called one-point compactification. Compactification. Later we're going to learn about a particular class of mappings that are rational functions called Mobius transforms. So and these are mappings like this. Z goes to AZ plus B over CZ plus D. Obviously, it's a rational function. In fact, it's the simplest rational function you could possibly come up with, right? Anything simpler than this would just be a polynomial. Yeah. And as we're going to learn, these mappings are, again, surprisingly wide and rich in their behaviors. There's a lot of stuff you can actually do with these mappings. And these things translate on as mappings of the sphere to itself. So these things will all translate as mappings of the sphere to itself of a particular kind. All right, cool. So that is that for this topic.